got my lab back to you.
So this week in lab, we're going to do experiment 4. It'll take, if everything goes well, it'll take about 4 hours or so, not the whole 5 hours. So you may have time to recrystallize your myristic acid if you haven't done so, possibly get melting points, weights, things like that, whatever you have left with experiment 3. So if you have enough time, you may potentially have an hour, maybe a little bit more to work on that kind of stuff at the end of the lab period. Otherwise, remember as we get down to here, experiment 3 report is due next week, so all of that needs to be done so you can hand in your report in lab next week. So if it doesn't happen in lab, it has to happen in open lab. But do at least, if you haven't done the recrystallization for experiment 3, try and get it done in lab this week. Okay, so then you don't have melting points and weights left. Your experiment 2 worksheets are due. The worksheets and the printouts of the menthol and morphine are due, going to be collected right at the start of the lab period. So make sure you have those ready to go. Make sure, I made this announcement the last few weeks, bring your calculators to lab. You need them, so bring them with you. You have a quiz this week, quiz number 4, and you also, if you haven't gotten it back, you'll get back experiment 1 report. Look at the report for feedback for future reports. This week, a little bit different schedule with open lab. So there is no open lab at all on Wednesday because of CIS. So there's no classes in session on Wednesday, therefore there's no open lab at all on Wednesday. Okay. There is open lab on Friday, but it's open from 9:30 in the morning till only 3 o'clock. It will not be open till 3:30. It is closing right at 3 o'clock on Friday. Okay. So keep that in mind. That open lab on Friday closing right at 3 o'clock. Next week, like I said, your experiment 3 report is going to be due, and then the report or the experiment we're going to be doing is experiment 6. On your syllabus, it talks about experiment 5 and experiment 6. The actual doing is experiment 6, and we'll talk about how experiment 5 comes into play next week. Okay, so if you're trying to prepare ahead before lab lecture next week, the actual doing comes from experiment 6. Okay, one other announcement that I couldn't kind of fit on there was just be careful when you're disposing your solid waste now. So once you've gotten your experiment 1 report, if everything was good, if your identifications of your unknowns were correct, you can dispose of your unknowns in the solid waste if you don't need those anymore, okay? You want to rinse those in with acetone to make sure that the solid itself dissolves in the, sorry, not in the solid waste, in the organic waste container. So your solids from experiment 1 can go in the organic waste container, but you want them dissolved going in, not just as solids, okay? Be careful, you don't want, we had a little bit of nutmeg in all sorts of places last week. So be careful, the nutmeg needed to go in the nutmeg waste container, not in the organic waste container. But your organic solids can go in there. Now, experiment 3, hang on to your myristic acid, your trimyristin, until you get your experiment 3 report back to make sure everything's okay with that, okay, before you dispose of those. Okay, so this week, we're going to be using a fractional distillation. And so we've already done one type of distillation. Now we're going to look at a different type. So first, what I want to do is just compare the two. So what does a simple distillation entail versus what is involved in a fractional distillation? Since you're already familiar with the simple distillation, having done it a few times. And so with a simple distillation, you really need a large range of boiling points to be able to use it as a separation technique. So it's used for separating something that's non-volatile from something that's volatile. Or I guess what it's coming off is the volatile, so it's better to say separating the volatile from the non-volatile. And so you need a really large range of boiling points to make this technique work. Usually you're looking at a difference between your volatile and your non-volatile. Your difference in boiling point is usually going to be probably about 100 degrees Celsius or greater. So you really need a large difference there in order for it to work. Otherwise, you may start distilling what you don't want to distill if they're a much smaller range. Whereas the fractional distillation, you can get away with a much smaller difference in boiling point. You could have about a 20-degree difference in boiling point and be able to separate things if you did a really good job with it, okay? And so what is happening with the fractional distillation is basically it's a way to do multiple simple distillations all at once, okay? And by doing that, you're getting better and better separation the more of those distillations that you do. So it's serial or a series of simple distillations. And it's all in one apparatus, so you don't have to like set up like a bunch of different apparatus. It's all in one apparatus. And a term that we'll introduce here with the simple distillations is something called theoretical plates. So the number of theoretical plates, I'll show you where that comes from here in a minute, is equal to the number of simple distillations that are occurring in that one apparatus. And so where this comes from is the very first fractional distillations. What would happen is you'd have this tube, so you'd be distilling up and back and forth through this tube, and the tube had glass plates on it. And so it was a surface for a boiling and condensing to occur, and then an actual, as you climbed this column, to actually get the actual distillation where the vapor would actually distill over. And so you had this column of these thin glass plates, and you would boil, condense, boil, condense, boil, condense, boil, condense, and as you went up, you were increasing the purity of whatever you were trying to distill. And the more of these plates you had, the smaller your difference in boiling point you could have for what you were separating. And so this is where the term theoretical plates came from, because you'd have a simple distillation occurring on each of these theoretical plates. Okay? In industry, they still use kind of a similar setup in industry. It's a huge column with these glass plates through that column if they had to do a fractional distillation. So like in the petroleum industry, when you get petroleum, you're distilling all sorts of things off of the petroleum depending on where it boils. And you do that by using a fractionating column. So to add theoretical plates, there's a couple ways we could do it. First of all, we could just have an open vertical condenser. So if we just, in our simple distillation apparatus, just added one more condenser to the apparatus but didn't put anything in it, that would add about 2 to 3 theoretical plates. And so just by adding that condenser, you would get better separation than just a regular simple distillation without it. If you actually pack something in that condenser, and this is what we're going to do, you get about 5 to 6 theoretical plates. So that's how we're going to add theoretical plates. We're going to add one more condenser, and then we're going to pack that condenser to make it add more theoretical plates. And so one thing that you want to consider is read in the lab manual, so I'm not going to go through all. In the lab manual, there's a big discussion around Raoult's law, so make sure you read over that in the lab manual. But that goes hand in hand with describing what is going on here and how we get purification by using a fractional distillation versus using a simple distillation. So a couple of the diagrams that are in the lab manual is, first of all, looking at a phase diagram. And we're looking at the vapor-liquid phases of something that is boiling. And so for this phase diagram, you've got a liquid that's made up of hexane and octane in it, okay? And the way that you read these is depending on what side of the diagram you are on as to what you're talking about that different liquid or vapor is composed of, okay? So if we start with this liquid here, that is 0.4 or 40% hexane, 0.6 octane, and we go up on the liquid side to our L1, that liquid at that mole fraction is about at 96 degrees. So its boiling point is about 96 degrees when it's 0.4 hexane, 0.6 octane, okay, or 4060, all right? If you go across the phase diagram to the vapor side, that vapor is actually 0.69 hexane, 0.31 octane. So it's more pure on the vapor side than the liquid was. Once it starts doing the distillation, it's purifying itself, okay? Then that vapor, when it condenses, is liquid 2 that has that same composition, okay? But then liquid 2 boils and forms vapor 2. Its composition is 0.87 to 0.13. So as you go down these steps of the phase diagram, you're getting greater and greater purification of your liquid, okay? And so each of these steps is basically a theoretical plate. That's what you're looking at, okay? And so you got to keep in mind what side you're on of the phase diagram, and then figure out by, first of all, what side you're on, liquid or vapor, and then looking down to what your composition is going to be, okay? And so, kind of a more real picture of what's going to be going on is, this is an example of the fractional distillation, okay? So we've got this liquid in here that is boiling at about a temperature of 96 degrees. It's 60 mole percent octane, 40 mole percent hexane, okay? So it starts boiling. Its vapor then becomes more pure than the liquid, and it's 31 mole percent octane, 69 mole percent hexane. So it's becoming more enriched in hexane. Then as you do another distillation, then you get to 13 mole percent octane, 87 mole percent hexane. And as you go farther and farther up, then you get that liquid purified to the point where we're about to distill it over. It's 2 mole percent octane, 98 mole percent hexane. Okay? So as it goes up the column, you are making it more and more pure of the two components. So you're getting more of one component and less of the other. Okay? The other thing to watch is the boiling point as you go up that column. Okay? So you're getting more and more enriched in hexane, while hexane's boiling point is lower than octane. So you're starting down here at a boiling point of about 96 degrees. Down, when you get up to this point, you've got a boiling temperature of 70 degrees. Okay? So it's close to hexane's boiling point because it's mostly hexane. So then, as it comes up and purifies, then we're going to have it condensed down, and we're going to collect fractions of this liquid as it's being purified to try and purify what you've got. So you're going to end up with this unknown that has two components in it, and we want to purify each component away from the other. All right? So the actual setup that we're going to use is going to look a lot like what is in your lab manual. And actually, before I show you the setup, let me show you. So here's a couple different types of fractional distillation columns. We're going to use the one that's packed with steel sponge, okay? So So we're going to just take our Liebig condenser and put some sealed sponge in it, all right? We could also take our Liebig condenser and just put some glass beads in it. That would also increase the reticle plates, okay? But it's kind of a little bit harder to keep track of all the glass beads, so it's easier to do this than this. If you can also just buy a fractionating column. So if you wanted to buy, they're called a Vigoro column. If you wanted to buy a Vigoro, you could do that, but they're really expensive. So we can't afford for all of you to have a Vigoro column in your glassware, okay? So that's why we've got to modify what we've got into a fractionating column. So what we're going to do is take kind of our basic simple distillation setup, and then we're going to add a few things to it, okay? So you're going to start with your 100 milliliter round bottom flask. You're going to want a stir bar in here and put this on a hot plate so that you can stir it, okay? Stir a hot plate. You're going to clamp your round bottom flask, and you're going to put in here your unknown, okay? You want to know the volume of your unknown before you put it in here. So measure the volume of your unknown, stick it in your round bottom flask. Then try and keep things as covered as possible because you're going to have this two-component mixture. One of them is going to be a lot more volatile than the other, so you can get good separation. But that means it'll also evaporate quickly on you. Okay, so you got to be really careful with it. Then you're going to have your Liebig condenser that you've already packed with steel sponge. So before you set anything up, you're going to pack your condenser. Okay. That condenser needs to be dry. The jacket, the inside of it needs to be dry, and the outside, the jacket, needs to be dry. So the way we will do that is inside, just make sure it's dried out. Outside, you can put some acetone through the jacket and then pull vacuum on it with the vacuum that's on your hood. That'll dry out that jacket and get all the water out of it. The reason for that is you don't want that heat to be doing something other than helping you have this fractionating column. So if you've got water in your jacket, the heat that you're going to make in this column is going to be used to vaporize the water instead of help distill and purify the liquids, the two liquids that you have. Okay, so it'll hinder your distillation if you have water in that jacket. Then the other thing is you need a clamp here, and you need a clamp here that's actually tight, and you want this as vertical, absolutely vertical as possible. Okay, you don't want it leaning over at all. You want it nice and straight and vertical. You're going to put a pipette bulb on the end of it, on either, and it can be on either end. The reason for the pipette bulb is you don't want air circulating. You don't want convection going through that column because that'll fight what you're trying to do as well. Okay, so you don't want air circulating through there as it's heating and cooling. So if you put a pipette bulb on there, you stop that circulation. Then you're going to put your three-way adapter on, and then your thermometer adapter and your thermometer, okay? So there is no water condenser, no water in or out connected to this condenser. It stays dry, okay? The one with the steel sponge is dry. Then you're going to come down to your water is going to go into your West condenser, your skinnier condenser, okay? Water in on the bottom, water out on top, just like before. And then you have this utility clamp here that's the looser clamp just there to support the condenser. It doesn't have to be super tight, okay? Come down to your vacuum adapter, and then instead of a round bottom flask, you're actually going to collect in your test tube. You're going to use your 10 milliliter test tube and your 25 milliliter test tubes. Okay, so you want those clean and dry, all right? Now, really key with this setup is your temperature, okay, and where that thermometer is. You're going to decide what these unknowns are based on some chemical tests that I'm going to talk about here in a little bit, and based on the boiling point of the liquid, the pure liquid, when it comes over, okay? So you need really good boiling point readings. You need that thermometer in just the right place, just under the arm of the three-way adapter, okay? So be really careful in your setup. The other thing that's really important, all these joints need to be sealed shut, because if you lose any of your liquid, you won't be able to measure how much you've collected, you won't be able to get the boiling point, and you won't be able to use it for the chemical test. It will all disappear on you and you won't have anything. And if you lose your unknown, it'll cost you 5 points to get a new unknown, okay? So it'll cost you 10% to get a new unknown. So you got to be really careful, make sure everything's good and sealed, okay? And remember, you're using 4 clamps with this setup. So one here, one here, one here, one here, okay? When you get it set up and are ready to heat and start the water, before you do that, have your instructor check your setup and make sure everything's okay, all right? Then what you're going to do is wrap this fractionating column with fiberglass insulation. So be really careful handling the steel sponge because it can cut you. Wear gloves. Be really careful handling the insulation because you can get fine little pieces of glass in your hand too. So wear gloves with it too. It'll get real itchy. You're going to wrap insulation to help keep everything nice and warm here so you're not losing heat as you're trying to get your fractions to come over in that distillation. Okay? Now, a couple other things with that distillation. When you're heating it, you're going to need, so everybody's got different unknowns, okay? So I can't say, turn your ohmite to 50 and then slowly climb from there, okay? You need to just slowly heat your, heat the heating mantle with the ohmite. And you need to be slowly turning up the heat, but you need to be persistent about it, okay? So you need to watch what's going on in your distillation apparatus. So if you turn on the heat, start about 50 or so, in a little bit you don't really see any boiling, then inch up the heat a little bit, okay? So keep watching what's going on in your distilling flask, okay? You need to watch what's going on and adjust the heat according to what's going on. So if you keep adding heat and after a little bit you're not boiling, keep adding a little more heat, keep adding a little more heat. You've got to be really careful not to go too slow with it, but you don't want to go so fast that you completely bypass your low boiling component and go straight to your high boiling component and never get any separation, okay? So you got to watch what's going on and you have to adjust it based on what's going on with your experiment, okay? After you are done with the experiment, that seal sponge now is going to have unknown on it, and these unknowns are pretty odoriferous. They've got a pretty strong odor to them, okay? So you don't want to just take that steel sponge out of your apparatus and take it out into the atmosphere of the lab, because the lab stink up pretty bad, okay? So make sure you rinse that steel sponge over your organic waste with acetone really well. Get all the residual unknown off of it. And anything that stinks, let's put it in garbage that we'll keep in the hood. So if your gloves end up stinking, paper towels end up stinking, have your instructor put it in garbage that we can stick in the hood, because otherwise the entire lab is going to be really stinky, okay? So if we bring it out of the hood, it'll be stinky. Try and keep all the stink in the hood. Then there's a container in the reagent hood for your steel sponge once you're done using it, okay? Once you've rinsed it out really well, then it goes in that container. When you are taking apart this apparatus, do it slowly. So don't say, okay, I'm done with the distillation, turn it off immediately, start taking things apart. It's going to take a little bit for things to cool off. So just let it cool down slowly, take things apart carefully, and keep in mind, unknown's going to be dripping throughout that apparatus. So wear gloves when you're handling it, don't get it on you, okay? You don't want to distill to dryness, okay? You could catch it on fire if you distill it to dryness, okay? So you want to keep an eye on what's going in your distilling pot. When you have a little bit of liquid left, then you're going to stop your distillation, okay? You're going to, once everything is cooled and drained, you will measure that volume, okay? And that volume is called the holdup volume. So that's what did not distill over. You'll end up accounting for that in the volumes that you are collecting, okay? But measure that holdup volume, okay? Then you're going to go through and do a series of chemical tests, all right? So what you're going to want to do before the distillation starts, in order to collect fractions, because you've only got 2 graduated cylinders and you're going to need to collect more than 2 graduated cylinders worth of material, is you're going to want probably about, I'd say probably about 5 to 6 small vials are clean and dry, okay, before you start the distillation. And the other thing with this cleaning and drying is you can't use acetone. One of the chemical tests reacts with acetone, so you'll get false positives for one of the chemical tests if you use acetone, potentially, okay? So you need to make sure everything's clean and dry, but do not use acetone when you're cleaning things, okay? So you're going to, as you're switching out your graduated cylinders, you're going to be putting your fractions into these vials and then getting the graduated cylinder back to, ready to go back on the apparatus again, okay? So you want to make sure, we don't want to cross-contaminate any of these fractions because it'll be hard in the end if you cross-contaminate to figure out which has the alkene and which has the alkane and arene that you're testing for, okay? So switch things out, make sure the grad cylinder is dry and ready to go back on the apparatus again before you do so, okay? And then you'll have all your fractions in these small vials and then cap them when you're done so you don't have your low boiling component especially evaporate on you before you can test it, all right? So what you're going to do is before you even start the distillation, you're going to be making a table and then eventually a chart in your, a graph in your notebook, okay? And so you want this table that I'm going to show you in your notebook before you start the distillation. So you're going to have in this table a column for temperature. And this is where you're going to collect all the data for your distillation. You want the volume collected for each fraction. This is per fraction. In milliliters. And then you're going to have a cumulative volume, so that's going to be the volume throughout the entire distillation. And then you're going to have a column for observation. So this is, like I said, where all the data is going to go for the distillation. Okay, so as you're writing in your notebook, everything that you would write down as observations or temperatures or things like that are going to go into this table. So don't forget, especially the observation side. A lot of times people do this experiment, forget to put observations in there. Okay, so you want to keep track of your observations. You want to be recording a temperature for, at the very most, each half a milliliter of volume that you collect. So either half a milliliter or even smaller volume that you collect, you want to be recording a temperature, okay? And so what that's going to look like is, say we've got this table going. So we've got all these temperatures recorded and the volumes that go with it. So at temperature 1, we have 1 milliliter, and then we have 1.5 milliliters in that fraction, and then we have 2 milliliters. And then all of a sudden we start to see a change in the graduated cylinder, or a change in the temperature. So then we start back at 0 milliliters, and then we have half a milliliter, okay? The cumulative volume for all of this is going to be 1 milliliter, 1.5 milliliters, 2 milliliters, 2 milliliters, and then 2.5 milliliters. So does everybody see how they're adding? This is per fraction. This is adding everything together. Everybody see that? Okay. And so here we've changed our fractions. You want to make sure it's very clear where your fractions start and end. So this dotted line is the difference between one fraction and the other. So things that you want to write down are things like, where did the ohmite start? What point did you have it set at? And where was it starting to heat? So say it was at 60 setting of 60, okay? At this point, at 1.5 mils, you've got constant collection of unknown. That's something you would want to write down, how the unknown is being collected. Here at 2 milliliters, we change our graduated cylinder. You want to write that down. And then all of a sudden we see here, at this point, we've got to increase the temperature on our oolite. And then maybe here, you know, we're starting to see like maybe a steadying of the temperature again into another fraction or something like that, okay? But you want to make sure that you're writing down all your observations. Write down what your oolite settings are. Write down what you're seeing with the distillation. Write down what's happening with the with the temperature, and when are you changing your graduated cylinder? All of those kinds of things, okay? And remember, you're every 0.5 milliliter, at least, if not smaller, you're making these notes and writing down the volume and the temperature, okay? So you need to fill this whole table, and it may go multiple pages in your notebook. And then, like I said, when you're done, you're going to measure the hold-up volume. So what's left in the distilling pot. And then what you need to do is you need to make a table of all this data so you can figure out what are your pure fractions that you collected, okay? So the table should look like this, and you may or may not, depending on the unknown, you may or may not with your table see what we call this forerun fraction before it gets up to a steady boiling point. You may totally bypass that fraction and go straight to your lower boiling component, okay? And hold there at a steady boiling point. Then you'll go to the mixed fraction, the fraction that goes from the lower boiling and climbs up to the higher boiling, and then hopefully you'll have your higher boiling fraction, and then you've got what's left, which will be the hold-up volume, okay? This is your ideal graph. This is what you want the graph to look like, okay? You want to see a nice climb straight to that lower boiling component where you don't lose very much volume. Then you go collect a significant amount of lower boiling component. Then you have the temperature increase of that mixed fraction, which is not very much volume. Then go to your higher boiling component, okay? To get a nice graph, you need to take lots of data points. So that's why I say take data at least every 0.5 mil, if not even less than that, every 0.3 mils or 0.2 mils, something like that. The more data points you collect, the better your graph is going to look. And the easier it'll be to figure out what's going on, okay? If when you're collecting data, if you have like a really sporadic temperature, it's going up, it's going down, turn up the oolite a little bit. Most likely what's going on is you're not getting enough heat to keep it at a constant temperature, okay? Same with in between fractions. You may not have it directly climb up to the higher boiling component. You may have your lower boiling, lower boiling, lower boiling. Then all of a sudden it drops down. That just means the lower boiling component's mainly off, and now it needs more heat to go up to that higher boiling component. So turn up that oolite, okay? So you really have to watch what's going on with your distillation and watch your data to see what you need to be doing with the heat. And don't necessarily pay attention to what's going on with your hood mate, because they have a different unknown than you do, okay? But in the end, this is what you want. So in your lab notebook, you'll want this table and you want a rough sketch of this, so then you can figure out what fractions contain your pure components, okay? So where we have a constant temperature is a pure component. And here for the lower boiling fraction, our fraction B and our fraction D would be our two pure fractions that we want to use, okay? So make sure you draw this in your notebook. For the report, you'll also make the computer generate this graph as well, okay? But for in lab, just hand draw it in your notebook, right? And before you determine anything, do not throw anything away either. Hang on to all of your fractions, okay? If you're not sure what's going on with the distillation, collect more fractions. It's always easier to combine things at the end than to not collect enough and then have to do the distillation again, okay? So if you're not sure what's going on, collect more fractions, not less, all right? But you should have a definite steady lower boiling component, definite steady higher boiling component, okay? So then, what we need to do is we need to figure out what unknown contains the alkene and what unknown contains an alkene or an arene, okay? And so we're going to do two chemical tests. We're going to do the bromine test and we'll do a potassium permanganate test. So with the bromine test, we've got two things that can happen. We can have electrophilic addition So we've got an alkene, so the bromine's going to react with the alkenes. So we've got our alkene here. Okay, this is our unknown. We've got an alkene fraction. It's going to react this way. So we're starting with something that's clear and colorless. All of the liquids are clear and colorless for the unknowns. Then you're going to add bromine to it. And this bromine solution is a red-orange color. What happens is that bromine reacts across that double bond, okay? As it's reacting, it's going to form a product that's clear and colorless, okay? So you start clear and colorless, you add red-orange. If it's reacting with an alkene, it's immediately disappearing as you're adding it, okay? So you're going to add bromine, it disappears, add bromine, it disappears, add bromine, it disappears. It's reacting, all right? And so what you get is bromine addition across that double bond. And in lecture, you're going to actually find out bromine adds this way, okay? When it adds across a double bond. It adds to opposite sides of the double bond, okay? And when you get to this in lecture, you'll discuss why that is. So, a positive test for the bromine test is you get the orange-red color fading, okay? With many drops. And so I'm talking like 20, 25 drops. When you're getting up there in the drops, you know, once you get to 25 drops and it still keeps going clear and colorless, that's a positive bromine test. You don't need to keep going until you get it to hold orange-red, all right? So if you keep adding, it still goes from orange-red to clear, orange-red to clear, orange-red to clear, 20, 25 drops in, you've got a positive bromine test, all right? But you're not going to have acidic vapors. So one of the things you're going to be testing with this is you're going to do this in test tubes, and as you're adding the bromine, you've got to be really careful not to get it on the pH paper, but you want to see if acidic vapor is generated from the test. You're not going to have you're not going to have acidic pH paper, okay? You're not going to have an acidic test. Or acidic vapors. This can react with acetone. So that's why you can't use acetone on any of your glassware this week, because you could get a false positive for the bromine test, okay? So you've got to be careful not to introduce acetone with anything that you're using this week. Don't rinse anything with acetone, right? And so it will actually react with the acetone itself, and then if you have enough acetone in there, you may think you have a positive test. Instead, it should be a negative result, okay? So it'll make things really confusing. Bromine can react another way, though, with what we're going to be using for our unknowns. We can also get a bromine substitution And this reaction is actually a radical substitution reaction, okay? And this happens with alkanes. So remember, your unknown is alkene is one component, and the other component's an alkane or an arene, okay? So it reacts also with alkanes. So if we've got this alkane, we can do a substitution reaction. And so instead of it adding, because we all have everything's saturated, we have all single bonds, what you get is in the presence of heat or light, and we've got definitely heat and light. We're going to be heating everything. Probably more the light after you're done though than the heat. You'll get the bromine substitutes out a proton. So you lose a proton for the bromine, all right? This guy, when you do the pH paper test, you get acidic pH paper. Okay? And usually you're not going to use as much bromine for this test because you're only adding 1 Br instead of 2 like above, okay? The thing to be careful with though is don't let this acidic pH paper be what lets you, don't let it be the deciding factor in whether or not it was a positive or negative test. Okay, you need to look at all of the data and look at how, if you think one, then it'd be not positive, but the test, so it's positive for an alkane, not an alkene, okay? You've got to look at all of both of your higher boiling fraction, your lower boiling fraction, see what happens with the bromine test, see what happens with the pH paper, and then see what makes sense for what's going on, okay? Don't let just what's happening with the pH paper be the decision that, oh, it must be reacting with an alkane, not an alkene, okay? Because the other thing that you need to do is we'll do a second test, potassium permanganate test, okay? So you're going to do this test on both your high boiling fraction and your low boiling fraction as well. So this time, we've got our alkene again. And again, remember, clear, colorless alkene. The potassium permanganate starts out, it's a purple solution, okay? Then, when it reacts with an alkene, in the presence we've got it made up of water, what you get is OH's, you get a diol that is formed from its reaction with the double bond, okay? And this is colorless, but what it also forms is manganese dioxide, which is a brown precipitate. Okay, and so what you're looking for is this purple color. When you add it to the clear colorless, first everything will be purple. What you should see is that purple fades, and you see the formation of the brown precipitate. That's a positive test, okay? If you have an alkene, you need a positive for both tests, okay? So that's why I was saying don't let this pH paper, the acidic pH paper, decide that it's an alkane, okay? Because if you've added a lot of bromine, sometimes that you can get false positives with the pH paper. You added a lot of bromine, it's still staying colorless. You also, in a separate test tube to the same fraction, added the permanganate. It started going colorless, and your brown precipitates, or the color at least started fading, you got brown precipitate. Then most likely you've got a positive for that fraction being an alkene, okay? The other thing with the permanganate test is it's not instantaneous. You need to wait a few minutes. So add the permanganate, wait 5 minutes or so, 8 minutes or so, and then see what you've got. And compare your fractions. Hopefully you've got differences between the fractions of one did change, one didn't really change, okay? So the amount of this color change can kind of sometimes vary too, okay? But you should see a change from the deep purple to kind of a more maroony, almost brown color, and then the brown precipitate, depending on how well it reacts, all right? Okay, the other thing, so we're gonna have alkenes. We need both positive tests, both chemical tests to be positive for it to be an alkene. Then your other possibility is alkanes or arenes. So, meaning it has a double bond, or sorry, it has an aromatic ring. Okay, what we are doing with these chemical tests will not react across the aromatic ring, okay? So you're not going to get a reaction on that aromatic ring under these test conditions. So if you get positive results for both tests, then that fraction is alkenes, okay? If you get negative for the test, then either it's an alkane or an arene, all right? So you're going to use these chemical tests, plus you need the boiling point information to then figure out what you've got, okay? And so in your lab manual, you've got a list of the possibilities for what could be in your unknown. Okay. And so some of these are alkenes, some of these are alkanes, some of these are arenes, okay? But you'll have an alkene and one alkane or arene, okay? So something, one of your fractions, your lower high boiling fraction should give positive tests for bromine and permanganate. The other fraction should give negative tests for bromine and permanganate, okay? Does everybody understand that? Okay. And it's these tests plus these boiling points that are important to figuring out what you've got. So in your pre-lab, you need to list all these possibilities, their boiling point, their density, what their chemical class is, okay, for your physical data table. You also need to list all of the stuff that you're going to use for the chemical tests. So make sure you include your solvents, everything that you need for the chemical tests, okay? This week, there isn't going to be a yield calculation, okay? So you won't have a yield calculation, but you will have reactions to show. You've got the bromine test reactions and the permanganate reactions. And you can show a flow diagram. And you have new equipment. You've got the fractional distillation apparatus to show, okay? As well as a reference, all right? So a little bit different than experiment 3 in that you don't have any yield calculations, but you do need to put this in your physical data table as well as everything, you know, including molecular weight, things like that, for what you use for the chemical tests reagents, right? And like I said, this is in your actual lab manual. So for what you will hand in for this lab, we're going to have unknown worksheets that you're going to hand in, okay? So you've got on page 417 and 418 in your lab manual, you're going to fill out these worksheets for each of your components, your low boiling component, your high boiling component, okay? All of the information, what happened, what was your boiling point range, what were your chemical test results, all of that information, what does the chemical test tell you about your unknown? Draw the structure of each unknown and give the unknown number. The next page, then you're going to, you want to attach a graph. So in this space, you want to give a nice Excel graph of your distillation. Okay, so you're going to put a rough sketch in your notebook, but you want a nice Excel graph right here that fits right here. So make sure you use an XY scatter plot for that graph that you're going to make in Excel. Then you need to answer questions about the components. So a couple hints here. At first looking at number 1 and number 3, it looks like it's the same question, but it's actually not. Question number 1, you're going to look at your low boiling component, so your low boiling fraction, your pure low boiling fraction, your pure high boiling fraction. You're going to look at the volumes of each of those. Add those two volumes together, and then you're going to take each individual volume divided by that total. So you're basically finding a ratio of what those volumes are, okay? So it should add up to 100%, these two numbers, okay? Number 2, you're going to calculate the percentage of original unknown that was collected in all of the fractions, not just the pure fractions, but all of the fractions. So what was your percent recovery? How well did you do on percent recovery for your distillation? Then number 3, you want to look at the percentage of original unknown that was recovered as pure product, okay? So your denominator here is what is your total original volume. Then take the volume of the pure low boiling component divided by that original volume. You get that percentage. The volume of the high boiling component times or divided by that original volume, you get the percentage of the high boiling component. Okay? So this number, these numbers, and these numbers are two different things. Okay? You're going through these calculations and you want to show all your work for these calculations on this page, because then you're going to write a conclusion where you address the points at the bottom. Okay? And you're going to word process this conclusion just like experiment 1 and experiment 3. You're going to hand in this sheet with your graph attached to your conclusion, and then your lab prof will tell you what you're going to do with your notebook. Okay? So write up your notebook like you normally would, because in some form it's going to be checked. But the big thing that's going to be handed in is this sheet, both sides completed, and your conclusion that should be about a page. You don't want to go much above a page. Okay? So that's what you will hand in.